Um, so why don't we all jump on? Let me grab this video link if you don't have the Google Drive up. I'll grab this video link for you guys. Watch this video real quick, and then we'll get into talking about pressure systems and altimeters and stuff like that. So uh, here's the link for you. It's also in your Google Drive onto yesterday's, because I thought we'd be covering it yesterday on yesterday's review. So everybody watch that quick 5-minute video, and we'll be back on in, let's just call it 5:42. All right, is everybody back?
I am back.
All right. So let's get a little more in depth with what that video just talked about. Oh my gosh. So he pretty much went over the same stuff that we started talking about last night, right? I said 3. I didn't think about the most the most uh, basic ones, AGL and MSL. But but yeah, forgot about 5. So it was close, right? 3, I talked about pressure out, indicated altitude, pressure altitude, and density altitude. Forgot to talk about mean sea level and AGL. Uh, so, but the point of what I was talking about stood still. It was still important. So, atmospheric pressure, it's one of the most basic variables used to describe the state of atmosphere, and is commonly reported with weather observations. So, like he's talking about in the video, um, these pilots are, if they're below 18,000 feet, are constantly um, getting updates on pressure changes as they fly, and that's due to the changes in pressure and what it does to our altitude. It's um, it's important because if one pilot doesn't change his altimeter, or if we're the pilot that don't change our altimeter, that ground's going to come up a lot quicker than we're expecting and can cause problems, right? Um, Not only that, but if we're flying, say the difference in general aviation uh, flying, um, we'll fly odd or even, just like the big jets flying much higher than us. Um, we'll fly odd or even, but we fly odd or even plus 500. So we maintain our our separation of 1,000 feet, but um, the problem is let's say one person came from one pressure system that was low and came into a higher pressure system, but the other aircraft came from a low pressure system and flew into that same high. Did I say that correctly? But what I'm trying to say is, if people aren't changing their altimeters, the potential, even though they're indicating the same altitude or the correct altitude that air traffic control may have gave them, they may be a lot closer uh, to each other than they should be, and it could cause things like mid-air collisions, or out at Salt Lake International, you got that really Ensign Peak, um, and that gravel pit that's right next to Salt Lake International. If you're not flying the correct altitude, you could easily, and it's low visibility, you could easily, you know, end up landing on the side of the hill rather than staying above it. So it's
Hey,
important.
Garrett,
Yeah.
Sorry to interrupt. You're talking about this, and I don't know if you're aware, there was a SkyWest crash out in Elko. If the information I have is correct, it directly applies to this. They they were in a Metro liner shooting an approach in I don't know if it was a heavy snowstorm, but light to moderate, and they impacted the hillside, just like you're saying right there. From what I understand, if you look at the NTSB report, it says that they just were not, the captain wasn't monitoring, the IFR procedures correctly. I believe what it really boiled down to, because they impacted the mountain on their approach, was they just hadn't set their altimeter, because otherwise everything was working. So it was just improper monitoring and, of the IFR approach.
Yeah.
You can look it up. But anyways, that's a SkyWest incident. I've got a NTSB. That report, I'll just put it right here in the chat.
Awesome.
There's a lot of other stories on it. Anyways, it directly applies to this kind of thing.
That's awesome. Thanks for the heads up there. So, yeah, it's actually a lot more common than people realize. The NTSB calls it controlled flight into terrain. It's the most common accident that they investigate, and a lot of times it's due from either flying the procedure incorrectly or not setting their altimeter correctly. So, it's an extremely important aspect of flying. So, yeah, I'll read through this NTSB report. Yeah, failure to maintain proper altitude during the approach. Factors related to the accident were terrain and weather conditions at the accident site. That sounds like the problem.
That was how it was explained to me one day when I was there talking to one of my crew members. He was pointing up at the mountain, and at that time he claimed that they actually impacted the VOR, so they were right dead on the approach, but just too low.
Mm-hmm.
I don't know if that's accurate or not, but that was part of the story I got on that day. Sorry.
No, I appreciate it. And we're gonna, like I said before, we're gonna look at some NTSB investigations as well in this class. Happened in January of 1990. Huh? That's crazy. But yeah, altimeter settings are also part of what we do as dispatchers. Is when we're setting our performance for when we're planning the flight and looking at performance, we're going to take barometric pressure into account when we're planning, just to verify that our engines are going to be able to perform, or if we're going to have weight restrictions or things of that nature. So let's talk a little bit about that parcel of air that I've been frequently referring to. So the atoms and molecules make up various layers in the atmosphere and are always moving in random directions. Despite their tiny size, when they strike a surface, they exert pressure. Right? Pressure, energy. So each molecule is too small to fill, and only experts exerts a tiny bit of pressure. However, when we add up all the pressures from a large number of these molecules that strike the surface each moment, the total pressure is considerable. This is the air pressure. So, have you guys ever driven down a canyon or up a canyon with a bag of chips, like a sealed bag of chips? Anyways, when you're driving up the canyon, because of the air pressure down in the valley, it's got a lot more air pressure where it was sealed than it does as you drive up the canyon. So as you drive up the canyon, the bag will continually expand. We even were driving up a Big Cottonwood Canyon up here in Salt Lake when I was a kid one time. We had a bag of chips explode in the car because it scared the crap out of us. We thought we had blown a tire or something. But yeah. But it's interesting though, as you drive down the canyon, you have the same thing but in reverse. If you have a sealed bag of chips and it expanded on the drive up, on the drive down, it's going to collapse basically. I want to show you guys. This is a lot easier to show you when you see it underwater. Trying to remember. So everybody, well, let's just, the atmosphere acts very similar to this. It's just with water pressure, you see it a lot more rapidly. So this guy's going to dive down. And follow this balloon. As the balloon gets deeper and deeper, the smaller and smaller it'll get. Let's see. This one doesn't show it as good as I.
This kid is the next Bill Nye.
Yeah. But what's interesting is as you rise to the surface, the balloon will expand. Let's see, what was the... So at 20 feet, the balloon's only 3 inches across. This is only 20 feet of water too. I've done this in 60 feet of water and it's pretty huge difference. And look how small the balloon is. As it gets closer to the surface, you'll see the balloon expand. But it's the same exact thing with air. You have the same problems. It's just in diving when you do that. Boyle's law, basically, is to show you that if you don't breathe on your way up, on your ascent, your lungs will explode. So that's basically how it concerns diving. But anyways, so basically the same thing in the air, right? The higher we go up, the bigger and bigger if it's in a vacuum, the bigger and bigger and bigger the air inside the vacuum is going to be. So, or I'm sorry, not a vacuum, but a sealed jar. So atmospheric pressure is the force per unit area exerted by the weight of the atmosphere. Since air is not solid, we cannot weigh it with conventional scales. Yet 3 centuries ago, Torricelli proved that he could weigh the atmosphere by balancing it against a column of mercury. He actually measured pressure, converting it directly to weight. So that's how we do it now, is with the barometer. So what he created was a barometer. Basically, it's an aneroid cell, and as it expands, the pressure increases. As it shrinks, the pressure the pressure decreases. So it's a flexible metal cell, and the registering mechanism. Air is taken out of the cell to create a partial vacuum. The cell contracts and expands as pressure changes. One end of the cell is fixed, while the other end moves, registering the mechanism. The coupling mechanism magnifies the movement of the cell and driving an indicator hand along a scale graduated in pressure unit. So just what I was saying, this aneroid cell will expand and contract, and it's just amplified by this lever system to give us a reading. And like it said in the video, all an altimeter is a barometer, but rather showing the changes in mercury or hectopascals. It shows us, it gives us a reading in feet in altitude. So it's the same exact thing though. So atmospheric pressure is expressed in many ways throughout the world. We've used millibars, or we'll use hectopascals. We use millibars in the United States. Hectopascals is what you're seeing here: 980, 990, 1000, 110, 120. Ours is, like I said, the standard pressure is 29.92 millibars. And then we'll see anything on either side of that. So once again, here's the chart. So in hectopascals, so our weather charts use the millibars. Hectopascals, it's basically the same exact thing. But then the way it's displayed in the cockpit, sorry, it wasn't millibars, it's inches of mercury. So, and then the other way we can see it is in PSI. So standard PSI is 14.7 pounds per square inch. So how does that relate to us? So here's New Orleans down at sea level, 29.92. It's at standard pressure. Up in Denver, where it's a mile high, right? Mile high city. So about 5,800 feet. The pressure, standard pressure up in Denver may be 24.92. So you can see pretty vast difference between the two different stations. So, yeah. So pressure variation, basically it's atmospheric pressure that varies with altitude, and the temperature of the air, as well as other minor influences such as water vapor. Changes with altitude as we move upward, like we were talking about last night. As we move upward through the atmosphere, the weight of the air above us decreases. If we carry the barometer with us, we can measure a decrease in pressure as the weight of the air above us decreases. So all it's showing us here, here's sea level pressure, 1,000, right? At 10,000 feet, we'll see a standard pressure of 700 millibars. That's 6, 5, 4, 3, 2, 1. The higher we get. Notice very similar to how water is, our greatest change in pressure is going to be in the first, I want to say it's the first 10,000 feet here. Yeah, the first 10,000 feet. So in water, the first 10 feet. Basically, the pressure being exerted on you is double what it is at the surface of the water. Well, in the air, it's at 10,000 feet. You're getting pretty close to doubling the amount of pressure felt on you. So, or I'm sorry, you're losing half the pressure because it's less dense. So reverse of water, but you're going to see the greatest pressure change in that first 10,000 feet. So temperature effects on pressure, like most substances, air expands as it becomes warmer and contracts as it cools. So down here, we'll show you a little bit, but so in the 3 columns of air, one colder than standard, one with standard temperature, and one with warmer than standard, pressure is equal at the bottom and top of each column. Vertical expansion of the warm column is made taller than the column for standard temperature. Contraction of the cold column has made it shorter than the standard column. So we can see that expansion and contraction here. Here's our standard atmosphere. You can see in cold air, everything's much tighter together. The air's more dense in cold air. Versus warm air, everything is expanded and a lot more. You'll have the same number of molecules in all of these, but it expands and basically has more room to move around in. And so that's why we're having worse performance in warm air, is because even though you have the same number of molecules, there's a lot more room for those molecules. They're not as close together as they are in cold air. It's much less dense. So there's less actual oxygen molecules that the engine's sucking in a given space. So sea level pressure, basically everything's dictated off of sea level pressure. Mean sea level is the most common reference. Pressure measured at the station at 5,000 feet elevation is 25 inches. Pressure increases about 1 inch of mercury per 1,000 feet, or a total of 5 inches. Sea level pressures is approximately 25 plus 5, or 30 inches of mercury. Okay, so that's how I figured out that calculation last night when I said we've got one station that may be 30.12, and then another station, when we fly to another station, we'll have 29.12. So that right there, the difference in the actual elevation of the field, pressure-wise. So this is talking about standard pressure, 29.12, or not bad. So let's make this easier. So 30.92, and here we have standard pressure of 29.92. Okay, so 29.92 is standard. This is our deviation from standard. So we take the difference here, and it's 1 inch greater. Okay, so at 1 inch greater, that's a total of 1,000 feet difference. So in Salt Lake, let's say that our deviation from standard is that 1 inch of mercury. And our elevation in Salt Lake is 4228, 4227. We add that 1,000 feet on there, all of a sudden, our engine is performing as if it was at 5,227 feet. So engine performance is going to get worse as pressure increases. Does that make sense? The video talked about this going from a high pressure to a low pressure. So let's say this is at 30.12 up here, but down here we have 29.92. Flying from a high pressure to low pressure without adjusting our altimeter, the pilot may think he's going to, if he's trying to maintain this altitude here, let's say this is 10,000 feet. If he's trying to maintain 10,000 feet and he does not change his altimeter from 30.12 to 29.92, then he's actually, he'll continue to correct. And as he gets closer to this area here, he's going to still be showing 10,000 feet in his cockpit on his altimeter, but he's actually going to be flying at 9,000 feet. So that's what it means by the high to low, look out below. The pilot's going to try to maintain his altitude, but without changing the altimeter to the correct altimeter setting. He's going to descend rather than maintain altitude.
At what point does he make that change in his altimeter setting?
Typically, what I do is whenever I'm transitioning from VOR to VOR, and when you're at 18,000 feet, it doesn't matter because everybody's got their altimeter set to 29.92, right? So if it were me and I had a VOR up on this hill and then a VOR up or down here in this valley, and I'm trying to maintain altitude along here, as soon as I hit the changeover spot, so let's say I'm halfway between the two, I'm going to be getting this VOR's. I'm going to be contacting this station and getting the current pressure setting or altimeter setting halfway between the two different stations, and that way I'm maintaining correct altitude.
So these VORs don't just send out a radio signal; they also provide the pressure.
Yeah. So it depends. A lot of the stations are equipped with what we call an automated weather observation system, or an AWOS, ASOS, or ATIS. If it's got one of those weather reporting capabilities on it, then we can get weather off of the different stations. So yes, they may have a VOR here, and then they have like the actual METAR machine sitting out here on the side of it, but using the same frequency, or not the same frequency, a different frequency. So let's show you what that looks like on a chart here. Let's go back to the VOR. So when you look on these maps, let me pull it up as if I were actually flying. You've got Wasatch VOR here. Well, on the side here, you can look at the different control towers. Down here. Okay, right here. So a lot of times these VORs are near an airfield, right? Here's all your ATIS frequencies. A lot of times also when, let's say I'm flying from Salt Lake to Ogden, or Boise to, let's say Boise to Ogden, okay? I'm over Boise, get my altimeter setting. I get over Idaho Falls, change it a little bit. I come down and I'm over getting close to Ogden. When I call into the Ogden and make my initial contact with the tower in Ogden, he's going to tell me, I'll tune in the ATIS frequency by myself, but the controller is also going to give me the current altimeter setting as well, just to make sure that as I get into a terminal environment, I'm up to date and have the correct altimeter setting. So let's see here. So these are the surface charts. On these surface charts that we were kind of looking at yesterday, I was showing you the low, high, trough ridge. So the trough is what we typically see, an elongated area of relatively low atmospheric pressure. A ridge is the opposite. It's a high pressure. This is a pretty basic view of one of those surface charts, but you can see the different areas of pressure. And something else that you can see as well, and how they identify a low and a high, because believe it or not, when meteorologists are looking at, reports and stuff, they're not going to see these L's and H's. So these isobars, what we call them, they're going to see what the pressure gradient is. Areas where there's a rapid change in pressure are going to be associated with a low pressure, whereas a high pressure, it's a very gradual change in pressure. So you can see these ridges here. You can see how it's very elongated area of high pressure, whereas the low, you can see these troughs here where it's the opposite of that. So a constant pressure surface along which the atmospheric pressure is everywhere equal at a given instant. So for instance, 500 millibar constant pressure surface has a pressure of 500 millibars everywhere on it. The height and altitude of a constant pressure surface varies primarily due to temperature. These heights can be measured by a raw insondi. I don't know how to say that. But basically what that is the National Weather Service takes routine scheduled upper air observations, usually referred to as soundings. So these are the weather balloons. They release them, and the sensor, as it travels up through the atmosphere, it's taking in data. It's checking pressure, temperature, relative humidity, wind speed and direction, and everything like that. They're also tracked with the GPS. So you can actually you can contact the National Weather Service and actually take part in releasing a weather balloon. It's kind of interesting. There's somebody I know at work that in their dispatch class they went and did a weather balloon release, but I think that'd be a lot of fun. Maybe I should look into that. But anyways, yeah. That's what the weather balloon looks like. That's the radio sonde looks like. So on the upper air chart, once again, they're measured using the weather balloons. So they're plotted on a constant pressure. Let's see. On a constant pressure chart and analyzed by drawing a line connecting points of equal height. These lines are called height contours. So these are the isobars, or the contours that you see on the chart I was showing you. So everything that we already talked about there. So a contour analysis shows high ridges, lows, troughs, aloft, and just as the isobaric analysis shows such systems at the surface, these systems have high ridges and low troughs are called pressure waves. Kind of like the tidal, or the tidal. What did they call them? Tidal waves, or tropical waves, down in the Caribbean. So yeah, basically the same thing as waves in the sea.
Quick question on that last little chart with the high and the low. You said that meteorologists don't always look at charts and see the H's and the L's there. Is it, would they be looking for the way that 540 and 546 line passes underneath from west to east because of the counterclockwise flow? It would be passing under?
So what they're looking at is right here, the low pressure you can see is centered over this area of the map, 534 millibars. But you can see the pressure gradient increases slightly, right? Whereas the high pressure starts at 552 and decreases slowly. So that's how they read. That's how a meteorologist is going to look at these gradient charts, and he's going to see where the pressure systems, where the increases in pressure, and how close the gradient is. And that's how he's going to determine where he's going to put that L, where he's going to put the H, things like that. But yeah, like we talked about before, the low is going to be moving counterclockwise and up, and the high is going to be turning clockwise and down. Did I answer your question or just add more?
No, it's you helped me to understand a little better. Thank you.
So density is the ratio of any quantity to volume or area it occupies. Atmospheric density is also or is defined as the ratio of mass or weight of the air to the volume occupied by it, usually expressed in kilograms per cubic meter. Okay. So remember how I said, and the video also said, density altitude is pressure altitude corrected for non-standard temperature. And we looked at these columns of air. So, and I even use, when talking about this, air density, right? The colder it is, the closer the molecules are together. Whereas the warmer it is, the further apart they are. So that's exactly what density altitude is, okay? We're looking at how many molecules are we getting into a specified volume, okay? So volume effects on density. The density of an air parcel varies immensely with the volume, assuming equal mass. An air parcel with higher density has a smaller volume than an air parcel with low density. Okay. So the shorter parcel has a higher density than the taller parcel, which contains a larger volume. This is due to the fact that the air molecules within the shorter parcel must be compressed within the smaller volume. Kind of self-explanatory there, right? Trying to cram the same number of air molecules just in a smaller space. So if you really want to know how to figure out the changes in density, in general, the density of an air parcel can be changed by changing its mass, pressure, or temperature. Boyle's law states that the density of an ideal gas is given by this. So
you will recall that some of us got D's in math, and I think this is the reason.
Yep, and this is the reason why I'm not going to go into that, because you'll never be asked to actually figure out, But Boyle's law, that's what we were looking at with the balloons, right? Going down underwater. So the density effects on pressure. Density is directly related to pressure, assuming a constant mass and temperature. An air parcel with higher pressure is denser than an air parcel with lower pressure. Okay. Like we talked about, air pressure decreases with the height in the atmosphere. Therefore, the density also decreases with height. In the atmosphere, pressure has the greatest effect on density in the vertical direction. Okay. Everything that I've already gone over. Even though, so you can look and see it a lot better here. Same number of molecules in a tighter space, right? And you just see it continually grow and get further out. It doesn't matter where you are in the atmosphere. The gases in the atmosphere that make up our atmosphere is 78% nitrogen, 21% oxygen. that is going to remain the same at any given altitude. Right? What changes is the amount of space between the molecules. So, when we talk about, or when you see these climbers that'll climb Mount Everest without oxygen, the reason why it's such a huge feat is because there's far less molecules in a given space than there are down here at sea level, right? So it's much more. It's a much bigger difference between the two altitudes due to the fact that it just spreads out more the higher we get. So the temperature effects on density. Density is inversely related to temperature. So it's directly related to pressure, but inversely related to temperature. Assuming that constant mass and pressure, an air parcel with higher temperature is less dense than an air parcel with lower temperature. This is because the warmer air occupies a large volume. Okay? So it's very similar to what we're seeing here. We have the same issue with temperature. Temperature basically will increase the volume of air. So you see an expansion rather than a contraction the warmer it gets. In the atmosphere, temperature has the most effect on density in the horizontal. So pressure, we see the difference in the vertical. Temperature, we see the effects in the horizontal plane. So there you go. There's the differences. So how does water vapor affect density? So density of an air parcel is inversely related to its quantity of water vapor. Water vapor is less dense than air with lesser amount of water vapor. This is because dry air molecules have a larger mass than water vapor and molecules. The density is directly related to the mass. Okay. So even though we can take the same volume of dry air and the same volume of moist air, because the water vapor itself is actually lighter than the air molecule, dry air is going to be more dense, or way more than moist air. Kind of interesting, huh? You'd think that it'd be the reverse of that. But it's not. So altimetry. The altimeter is a barometer. This is what we talked about. And we talked about these different types of altitude, right? So true altitude is actual vertical difference or distance above mean sea level. So that's taking everything into consideration: pressure, density, spitting out an actual altitude above sea level. Indicated altitude is what the pilot's seeing on the instrument, right? That's what he is looking at in the cockpit. So altimeter settings. Since the altitude scale is adjustable, the pilot can set his or her altimeter to read true altitude at some specified height. So this is everything that we've already talked about once again. Making sure that the pilots are changing the altimeter as they move across the country. Super important. And these graphs just kind of show you what happens as we move from colder air to warmer air, or vice versa, or from a high pressure to a low pressure. So it's just a visual of everything that we talked about. So corrected altitude is just when the pilot corrects the altitude. So if a pilot could always determine mean temperature of a column of air between aircraft and the surface, the flight computers would be designed to use this mean temperature in computing true altitude. However, the only guide a pilot has for the temperature below him is free air temperature at his altitude. Oh, excuse me. Therefore, the flight computer uses outside air temperature to correct indicated altitude at the approximate true altitude. So we can only get so close, but with everybody on the same altimeter setting, we're going to maintain our separation. In the standard atmosphere, sea level pressure is 29.92. Pressure decreases at a fixed rate upward through the standard atmosphere. Therefore, if the standard atmosphere is given pressure exists at any specified altitude, the pressure altitude is the altitude above sea level shown by the altimeter when it is set to 29.92. As we discussed earlier, constant pressure surfaces have different height across them. Therefore, when flying at a specified pressure altitude, a pilot's true altitude will change with the distance. However, since pressure altitudes are flown at or above 180 or 18,000 feet, a pilot will always or almost always be above the highest terrain features. So that's why when we get to 18,000 feet, we switch to a standard pressure of 29.92 is because we don't have to worry about terrain for the most part above that flight level. If we didn't have to worry about terrain, we wouldn't have to worry about our altimeter, right? Let's see. Why don't we take a 10-minute break and jump back on. Let's make it 14 minutes just to round it off. Let's jump back on at 7 o'clock on the dot.
Yeah, that's crazy.
So I liked how on that video link, the guy kind of talked through what we've been talking about, right? Everybody hear me?
Yep.
Yes.
Phones are being weird. Hold on. All right, can you all hear me?
Yeah.
So, yeah, it's crazy what a difference, density altitude can make. I mean, technically, that pilot should have aborted that takeoff long before he ever got to that point. See some of the human factors come into play there. Thought, it's probably an old farmer that's flown that hundreds of times, but conditions changed, and all of a sudden things didn't want to work the way they're supposed to. But as it says here, the pilot cannot detect the effect of high density altitude on his airspeed indicator. The aircraft lifts off, climbs, cruises, glides, and lands at the prescribed indicated airspeeds, but a specified indicated airspeed, the pilot's true airspeed and ground speed increase proportionally as density altitude becomes higher. The net results are that high density altitude lengthens a pilot's takeoff and landing rolls and reduces his or her rate of climb. Before liftoff, the plane must attain a faster ground speed and therefore needs more runway. And the reduced power and thrust added a need for still more runway. The plane lands at a faster ground speed and therefore needs more room to stop. So, all bad, right? Yeah. I mean, 9,100 feet, that's pretty high up there. And we pretty much saw exactly what this is showing us. It's a lot. That video did a lot better than these graphs do. So this is talking about high density altitude can also be a problem at cruising altitude. When the temperature is higher or warmer than standard atmosphere, the higher density altitude lowers the service ceiling. So basically, we're not able to climb as high. Right? If the temperature at a pressure altitude of 10,000 feet is 20 degrees Celsius, density altitude is 12,700 feet. A pilot's aircraft will perform as though it were at 12,700 feet, indicated at a normal temperature of -8 degrees Celsius. To compute density altitude, a pilot can set his altimeter to 29.92 read the pressure altitude from the altimeter, and then obtain outside temperature and use a flight computer to compute density altitude. All of which we don't really care about because we don't sit in the cockpit. So that
I do recall as I was setting the altimeter in the 182, for example, it would give me a reading whenever I'd get the pressure that day that I was going up. I would set the altimeter. Normally, I believe the airport was right at about 2,520 feet. This is the old airport. And whenever I'd set that up or down, it would change the actual indicated height of the runway to what we could expect. So it's starting to make some sense again.
Yeah. In fact, when you're sitting on the ground at an airport, it's really easy. You don't need to get the actual weather report to know what the pressure setting is. All you need to do is, let's see if I can pull up a visual aid here. I hate this thing. So this is what an altimeter in a cockpit kind of looks like, right? So you turn this knob and it changes this window here. This tick mark here is indicating which pressure setting you're at. So all you have to do is you get the altitude, you look at the airport chart and you get the altitude for the airport. So let's say it's Salt Lake. I can't remember if it's 27 or 28 at the airport today for some reason. So 4227, let's say that's what it is. All I would do is I would turn this knob until my altimeter was reading 42. The long arm was pointing at 4227. So I'm sorry, let me erase this here real quick. So this arm would be pointing somewhere right there. And whatever I read right here, that would be my pressure setting. So basically I tune, rather than getting the pressure from Salt Lake Tower, I would just do the reverse and I would set the altimeter to my current altitude and then read it off of here. Does that make sense? So as we turn this knob here, this needle will rotate like a clock, right? So yeah.
And vice versa. If you tune it to the altimeter setting indicated over the radio, it should give you your indicated altitude.
Yeah, exactly. So when you're in the air, you have to get the radio report as to what the altimeter is, because we don't know our true altitude when we're up in the air, right? We have to set our altimeter to that. We have to calibrate the altimeter to read the correct altitude. But that finishes up our altimeter. So wind. Let's talk about wind here. Naming the wind. Wind is named according to the direction from which it is blowing. For example, west wind indicates the wind is blowing from the west to the east. In aviation, 36 points of the compass are normally used to represent the direction from which the wind is blowing. For example, north winds come from 360 degrees. East winds come from 90 degrees. South winds come from 180 degrees, and west winds come from 270. So forces that affect winds. 3 primary forces affect the flow of wind: pressure, gradient force, Coriolis effect, and friction. Okay. So let's talk about the first one, pressure gradient force. So it's exactly what we were looking at on the previous ones. These gradient forces here, right? So on the high, it's pushing out. Low, it's pushing in to the center. So think of a high as like a peak. High. Think of a low as a valley. Okay. So the high's coming down, and the low is going up. Remember, our rotation is clockwise and up. Our low is, our high is clockwise and down. Right? So that pressure gradient is what's creating the wind. It is one of the forces creating the wind. So whenever a pressure difference develops over an area, the pressure gradient force makes the wind blow in an attempt to equalize the pressure differences. This force is identified by height contour gradients on constant pressure charts and by isobar gradients on surface charts. So basically, the higher speed winds are going to be with a tighter pressure gradient force. There's lower speed winds when there's more spacing between the gradients. It's going to be a much more calm wind. Okay. So pressure gradient force is directed from a higher height pressure to a lower height pressure, and is perpendicular to the contour isobars. Whenever a pressure difference develops over an area, the pressure gradient force begins moving the air directly across the contours isobars. Okay, so wind speed is directly proportional to the pressure gradient force. And as I said before, the closer the isobars are together, the higher the wind. The further spacing, the lower speed wind. So the second force that's acting and creating wind is the Coriolis effect. So a moving mass travels in a straight line until acted upon by some outside force, right? Now, isn't that one of the Newtonian laws? One of Newton's laws of gravity. So, however, One is viewing the mass from a rotating platform. The path of the moving mass is relative to its platform appears deflected or curved. To illustrate, consider a turntable. One used a pencil or a ruler to draw a straight line from the center to the outer edge of a turntable. The pencil will have traveled in a straight line. However, stopping the turntable, it is evident that the line spirals outward from the center. Right? You guys ever play with those as kids, where you'd spin the disc and you'd draw all these random spirals and stuff? Little did you know that you were exercising what the Coriolis effect is. See, all these toys as a kid are actually grown up, like took scientists hundreds of thousands of years to develop. Okay, not hundreds of thousands, but hundreds and thousands of years to develop. Gyros, I remember playing with those as a kid. I thought they were really cool. Looking at these spiral, I can't remember what they call them, spirographs or something like that. You're actually playing with one of Newton's laws. So because the Earth is spherical, the deflective force is much more complex than a simple turntable example. Three-dimensional, right? Although the force is termed apparent to us on Earth, it is very real. The principle was first explained by the Frenchman Gaspard Gustave de Coriolis, and now carries its name, the Coriolis effect, or Coriolis force. So the Coriolis force is at a right angle to the wind direction and directionally proportional to the wind speed. That is, the wind speed increases, the Coriolis force increases. So similar to what we were talking about yesterday, right? Depending on the distance from the equator, the greater the effect, right? And depending on our direction as well. So this graph just kind of shows you the different effects of the Coriolis force at different directions, different latitudes. So kind of interesting, right? So as you can tell, kind of different from the pressure gradient force. With the pressure gradient force, it was the wind traveled directly proportional. With the Coriolis effect, it's 90 degrees off, right? So Coriolis force is pulling down, and the wind will move 90 degrees perpendicular to the Coriolis force. So the Coriolis force magnitude is directly proportional to wind speed. The wind speed is twice as strong in the right panel, thus the Coriolis force is doubled. So the actual speed of the wind is proportional to the force of the Coriolis effect. And of course, just to throw in another thing, friction force. So friction between the wind and terrain surfaces slows the wind, right? Putting your hand outside the window and putting it perpendicular, there's a lot more friction. Therefore, it's a greater pull on your hand. Whereas if you turn your hand parallel to the ground, then then there's not as much friction, and so the wind, yeah. So the rougher the terrain, the greater frictional effect. Also, the stronger the wind speed, the greater the friction. Okay. One may not think as friction as force, but it's very real and effective force as always acting opposite to wind direction. Okay, so it's the thing that's pushing back. Frictional drag on the ground normally decreases with height, becoming insignificant above the lowest few thousand feet. However, this may vary somewhat since both strong winds and rough terrain extend the friction layer to higher altitudes. So upper air wind, you can see the pressure gradient force is pushing up. Coriolis is pushing 90 degrees perpendicular, and then the friction force is pushing inversely, or 180 degrees from the wind. Okay. So upper air wind, the atmosphere above the friction layer, lowest few thousand feet, only the pressure gradient force and the Coriolis force affect the horizontal motion of the air. Remember that the PGF drives the wind and is oriented perpendicular to the height contours. When the PGF is first established, the wind begins to blow from higher to lower heights directly across the contours. So the Coriolis force deflects it to the right. Soon the wind is deflected a full 90 degrees and parallel to the contours at this time. Coriolis force exactly balances pressure gradient's force. With the forces in balance, the wind will remain parallel to the contours. This is called geostrophic winds. So, as everything levels out here, it all equalizes. And that's when we have what we call a geostrophic wind. Okay, surface wind, a lot different here. At surface, all three forces come into play. Frictional force slows the wind speed. Coriolis force decreases. However, the friction does not affect PGF. PGF and Coriolis force are no longer in balance. The stronger PGF turns the wind at a right angle across the isobars toward the lower pressure until the three forces balance, as shown in figure 710. There you go. Yeah. Trying to pick out the parts that are a little more essential. So polar cells, air rises, diverges, and travels towards the poles, kind of like we showed in the previous advisory circular that we looked at yesterday. So once the air sinks, once over the poles, the air sinks, forming polar highs. At the surface, the air diverges outward from the polar highs. Surface winds at the polar cells are easterly, okay, polar easterlies. So traveling east. Between each of these circulation cells, bands of high and low pressures at the surface. The high pressure band is located about 30 degrees north or south latitude and at each pole. Low bands are found at the equator and 50 degrees or 60 degrees south. So 50 degrees north, 60 degrees south. So you can see that here. Low pressure band, low pressure band, high pressure band. So we looked at yesterday. We looked at the tropical winds and trade winds and stuff. Well, where do you think the jet stream forms? It's going to be between jet stream forms between these different cells here. Okay, that's where we have the high pressure and the low pressure meeting together and accelerating the wind through the different pressure gradients, right? So jet streams. Relatively narrow bands of strong wind in upper levels of the atmosphere. The wind blows from the west to the east in jet streams, but the flow often meanders southward and northward in waves. Jet streams follow the boundaries between hot and cold air. Since these hot and cold air boundaries are most pronounced in winter, jet streams are the strongest for both northern and southern hemispheres in the winters. Okay. Let's take a quick look. We've actually got a chart that shows us the jet streams. So this is what we call a winds loft chart. Okay. These areas right here with the blue shading, okay, everybody see those? Goes from a blue to a magenta. These are the jet streams. Okay. You can also see a jet stream down here. Let's check out a couple different flight levels. So looks like it's strongest about 34,000 feet here. But yeah, extremely high winds. So just for reference on how to read this chart, and we're actually going to look at these charts and learn about them. These flags that we see here each represent 50 knots. So the wind speed right here would be 50 knots. These are each 10. So 10, 20, 30, 40. And then this shorter bar here is 5 knots. So 145 knots. Getting into those jet streams makes the flight super nice. Ooh, it's starting to become summer. Looks like some fun stuff. Looks like I might have a crappy day tomorrow. Or not tomorrow, but maybe Saturday. Feel bad for people at work right now. So direction flow. Why do the jet stream winds blow from west to east? As stated in the previous section, if the Earth was not rotating, the warm air would rise at the equator and move towards the poles. The Earth's rotation divides the circulation into 3 cells. Likewise, the Earth's rotation is responsible for the jet stream. Motion of the air is not directly north and south, but rather is affected by the momentum of the air. Momentum the air has as it moves away from the equator, and how fast the location on or above the Earth moves relative to the Earth's axis. So, depending on basically the Earth's axis, the rotation, which is constant, right? Depending on the location, that's going to determine the speed of the jet stream there. So an object's speed relative to your Earth's axis depends on its location. Sometimes standing on the equator is moving much faster than someone standing at 45-degree latitude line. If the person at the position on the equator arrives at the yellow line sooner than the other two, someone standing on the pole is not moving at all. The speed of the rotation is great enough to cause the person to weigh 1 pound less at the equator than he or she would at the North or South Pole. Pretty weird, huh?
So instead of the South Beach diet, this is called the South Pole diet?
Yeah, exactly. It's only 1 pound, so I don't know that it's worth freezing your butt off, but whatever. So does this make sense, this graph here? So the rotation at the equator is quicker than the rotation at 45 degrees north latitude.
Even though the circumference of the Earth is wider at that location?
Yes. And that's, so it's, so what it's saying here is the person, let's say we have people standing at each one of these points. We've got one person standing on North Pole, 45 degrees, and the equator. Let's say they're trying to get to this straight line point right here. Okay, this person's just going to spin like a top. this person's going to reach the line the first because of, maybe it'll help. Let's put America here, right? So that's really bad America. And here's Europe, right? So anyways, this guy's going to reach this point due to the curvature of the Earth. It's
Hey, I'm tracking.
I'm not. I confuse myself more than I do any good, I swear. But
So is that why air is more stable? High pressure is up at the North Pole because there is a lot less rotation going on up there?
That's part of it. Also, the big thing is, like it shows here, the troposphere, or where most of it is being generated, most of those weather systems and winds and things like that are being generated, is a lot smaller. So there's a lot less ability to accelerate or to build storm systems. You can also see that due to temperature is a huge factor in storm systems and winds and things like that. Where we have the greater ability, because of how close the equator is to the sun relative to the North Pole, the heat, we get a lot more of that convection going on. Whereas the northern latitudes here don't have as much of that heating as the equator does. So part of it is the speed of the rotation. The other part is the height of the troposphere and the heat, the amount of heat. So like you were saying, Rex, right here. So the momentum of the air as it travels around the Earth is conserved, which means as the air that is over the equator starts moving towards one of the poles, it keeps its eastward motion constant. The Earth below the air, however, moves slower, and as the air travels towards the poles, the result of that air moves faster and faster in an easterly direction the farther it moves from the equator. I guess that's not really tying in the way I wanted it to. So this is where we tie in. Okay. So location. In addition to the 3 cell circulars mentioned previously, the regions around 30 degrees north-south and 50 to negative 60 north-south are areas where temperature changes are the greatest, as the difference in air temperature between the 2 locations increase, the strength of the wind increases. Therefore, the regions around 30 degrees north-south and 50 to 60 degrees north-south are also regions where the wind in the upper atmosphere are the strongest. So where we see the strongest wind is actually going to be between these two. This polar jet here. So the jet stream right there versus this jet stream. So as far as weather development, we're going to have much more closer to the equator, but the higher wind speed here due to the height and the temperature differences between these two cells here. Okay, this is where we see that greatest temperature change. So the height of the jet stream, that's what it's talking about here, varies greatly between the polar jet and the subtropical jet. Subtropical jet may, jet streams may vary in height from 4 to 8 miles and can reach speeds of more than 275 miles per hour, or 239 knots. The actual appearance of jet streams is the result of complex interactions between many variables, such as location of high and low pressure systems, warm and cold air, and seasonal changes. So they're not, contrary to this picture, they don't just sit in the same latitudes. It's going to vary depending temperature, seasons, Earth's rotation, things of that nature. So the jet stream also follows the sun, and that the sun's elevation increases each day in the spring. The jet stream shifts north, moving into Canada by summer. As autumn approaches, the sun's elevation decreases and the jet stream moves south to the United States, helping bring colder air into the country. I already showed you the jet stream on a chart. So that's talking about what we were, compare it to a river, right? The strongest current is typically in the center of the river. It slows as it goes to the banks. It's the same as the jet stream. The center of the jet stream is going to be where the strongest winds are, which was also apparent in that chart I showed you guys earlier. Saw the blue area, and then it went to the magenta in the center of the jet stream. So the higher speed winds were in the center. So local winds. So local winds are small-scale winds, wind-filled systems driven by diurnal heating or cooling of the ground. Air temperature differences develop as over adjacent surfaces. Air in contact with the ground heats during the day and cools during the night. Low-level pressure gradients develop with high pressures over the cooler, denser air, and lower pressures over the warmer, less dense air. So this is basically how it looks. And this is also why we see, as the sun's coming up, we can basically see the weather follow the sun, right? All of a sudden we have big temperature differences in the surface as we move, as the sun starts heating the ground. And generally, remember, we see weather where a low is coming in contact with the high pressure. So we'll see the cloud formations along these points, cloud or fog. Okay. So as the sun's rising, we've got a cooler surface. We've got a warm surface over here. The warm air surface, we get rising action. As it moves to the high pressure, we get a lower, a cooler air. It cools the air and falls here. So low-level winds develop in the direction of the pressure gradient force. Coriolis force is insignificant because of circulation's dimension, less than 100 miles, and because of its lifespan. So thus, the wind generally blows from a high-pressure cool surface to a low-pressure warm surface. Air rises over the warmer surface and sinks over the cooler surface. Local wind circulation is the easiest to identify when a synoptic scale wind patterns are weak. So these are the type of winds associated with the low-level winds. Sea breeze, land breeze, lake effect, valley breeze, mountain plains, and wind circulation and mountain breeze. So in Salt Lake, we get a lot of this lake effect. We also get a lot of this mountain breeze as well. Get a lot of this lake breeze and lake effect over in the Great Lakes area. But some of the hazards, get a lot of turbulence, right? Whenever we have this rising action, this is where the turbulence is going to lie. When we get this warm surface, it generates what we call thermals, or pockets of air rising rapidly. Okay, so this is where turbulence is going to form, is during this part right here. So let's see. So, like I said before, also clouds and precipitation, including thunderstorms, can develop in the rising air over the warmer surface given the sufficient moisture in there. So sea breeze, let's talk about what sea breeze is. Sea breeze is coastal local wind that blows from the sea to the land, okay, caused by the temperature differences of when the sea surface is colder than the adjacent land. These sea breezes usually blow on relatively calm, sunny summer days. Okay, the cooler seawater comes in contact with the warmer ground and rises, and then we get this circulation pattern formed. Okay, air above the land becomes warmer, less dense than the air above the water, and this is because the land heats up faster than the water. Low-level pressure gradients develop with low pressure over the warmer land and high pressure over the cooler water. Okay, so low pressure, high pressure. You see that circulation form. So sea breeze front is when the horizontal discontinuity in temperature and humidity that marks the land edge of the intrusion of cooler moisture-bearing air is associated with sea breeze often produces a wind shift, enhanced cumulus clouds along its leading edge. Cumuliform clouds may be absent and air mass being lifted over the land is dry or stable. So if we have this the sea breeze, it has the potential of creating a frontal system, right? And like I said earlier in the class, the low pressure, where we tend to see weather form, is the warmer fronts, the warmer areas coming in contact with these colder or high pressure fronts. So as the high pressure tries to push under the low pressure, we see this rapid rising action right on that frontal system, which creates these cumuliform clouds. Okay, cumulus clouds. Just think of those as the clouds that look like. So cumulus clouds are like the big fluffy clouds that you see, right? When we get a towering cumulus cloud, what that kind of looks like is the cloud will kind of come up like this, and then it'll anvil top, is what we call it. Okay. That's and they're generally pretty extreme in how high and how tall the cloud is. Normal cumulus clouds, back in elementary days, that's what a cumulus cloud looks like, right? When we get these towering cumulus clouds, generally the cloud depth or thickness here or height is going to be, up in the teens and 20,000 of feet tall, whereas these other cumulus clouds are probably 2,000-3,000 feet thick. So towering cumulus clouds. Stratus clouds are just kind of those blobs in the sky at lower altitudes. A little smoother, not really fluffy. Okay. Cirrus clouds are the clouds that are high altitude here, just kind of like little fluffs up at the higher altitude. You also get cirrus clouds, we call them mare's tails, where they're just kind of wispy and long like that. Those are cirrus clouds as well. So just a quick crash course on clouds. So cumulus clouds we associate with turbulence or a lot of rising convective activity. Okay. So these sea breeze.
Might we be able to do a bathroom or dinner break?
Sorry. Yeah, we'll. You guys want to do dinner break? Let's jump back on at 8:40. How about that?
Okay, thank you.
Yep.
I'm back.
All right. Man, I'm all kinds of out of breath now. Like working on prepping our house to sell. So your dinner breaks are my work breaks. Let's see. So let's talk about. I'm going to talk about sea breeze and sea fronts. Let's talk about the coastline shape and how it affects it. So locally, the shape of the coastline plays an important role in the development of convection along sea breezes. A narrow peninsula or island is generally an area of strong convection or convective development during the late morning or early afternoon. This is because a sea breeze formed along opposing shores merge near the peninsula or island center. So perfect example of this is San Francisco. During the late morning, we almost always, very routinely see fog banks roll in on San Francisco, or low vis due to thunderstorms or whatever. In San Francisco, big problem there. So this is just kind of a graph of what it's talking about. So where we have the two different bodies of water, we have sea breeze opposing each other. When they converge, we see heavy convective activity. So somewhere else that we see this a lot would be places like Seattle. Seattle, it rains almost on a daily basis, right? So convergence occurs where the sea breezes merge from opposite directions. Strong lift may be sufficient to initiate showers and thunderstorms if the air mass is sufficiently moist and unstable. So let's talk about land breeze now that we've covered sea breeze. Basically the reverse of sea breeze. Land breeze is a coastal breeze blowing from the land to the sea caused by temperature difference. When the sea surface is warmer than the adjacent land breeze usually occurs at night and during the early morning. Okay. So the exact opposite of a sea breeze. So lake breeze, I don't know. Do you feel like we need to spend any more time on land breeze? I don't think we do. Just know that it's exactly opposite of a sea breeze. So a lake breeze is a local wind that blows from the surface of a large lake onto the shores during the afternoon and is caused by temperature difference when the lake's surface is colder than the adjacent land. So just like the sea breeze, but a big lake causing this. Like I said before, it's most common in the Great Lakes area. Both occur during the warm season, primarily spring and summer. Both are easiest to detect in light synoptic wind conditions. So there you go. So here's the difference between the lake breeze. Is it almost is always associated with the line of cumulus clouds, right? Talked about this when we were talking about sea breeze fronts or sea fronts. Almost identical situation. Two bodies of warm land on either side of the large body of water. Cold water. As the cool air descends or the high pressure descends over the cold water, pushing the colder air across the warm land and developing these areas of high convection. Remember, the low pressure is always trying to overtake the high pressure. And so we see this rapid forming of convection occur when this happens. So as with sea breeze, thunderstorms are favored in the upward motion branch of the lake breeze circulation. This is especially true where breezes from adjacent lakes collide. So examples of this would be Lake Erie and Lake St. Clair. And many of the other Great Lakes, and that's why we see this mostly in those areas, is due to how close the lakes are to one another. And you can see right there. So we see the real high buildup of convective activity on either side of the lake. What's really interesting about this is you can see the lake breeze over both the lakes completely clearing it of clouds. But on either side of Lake Erie here, you see just massive thunderstorms built.
That particular area you're looking at right now is an area that my wife and I have spent a lot of time at during the spring and summer. And almost every time it's cloudy and rainy there.
Yeah. Yeah, and that's due to the lake breeze. And especially bad due to the proximity of the two major lakes, right? So valley breeze, as you can see here, this is something that happens a lot in the Salt Lake Valley as well as places like Denver. But a valley breeze is a wind that ascends mountain valley during the day. Air in contact with the sloping terrain becomes warmer than the air above the valley, and this is because the air contact with the sloping terrain heats up faster than the air above the valley. So remember when we were talking about winds, we talked about friction. Friction generates heat. Heat causes this rapid rising of warm air, okay? So as the air, we have this air that pushes through the valley as it climbs the mountainsides. It's rapidly heating up. And you'll always see these lines of cumuliform clouds at the tops of the mountains when this happens. But yeah, basically it's just the hot air getting hotter as it ascends the mountain. So pressure gradients develop with lower pressure over the warmer sloping terrain, and higher pressure over the cooler valley winds develop in the direction of the PGF. Thus, the wind blows from the valley up the mountain slopes, air rises over the sloping terrain and sinks over the valley. Clouds and precipitation may develop over the mountain slopes. Okay. Mountain plains wind system. Okay. Again, something that we see in Denver a lot. But basically, there's a lot of circulation of air here. Once again, the air warms as it's ascending the mountains, but the air direction of the cooler air is perpendicular, perpendicular, yeah, to the, not perpendicular, reverse course, I don't know, to the warmer area or air below. So during the daytime, the wind system is the equivalent of 1/2 the valley breeze. Air in contact with the sloping terrain once again becomes warmer and less dense than the air above the plains. This is because the air in contact with the sloping terrain heats up faster than the air above the plains. Okay. PGF develop with low pressure over the warmer sloping terrain and high pressure over the cooler plains when developing in the direction of the PGF. Thus, the wind blows from the plains up the mountain slopes. There's a weak return of flow aloft. Clouds and precipitation may develop in the rising air over the mountain. What happens is as this builds and gets stronger and stronger, we'll start seeing things like rotary clouds or mountain wave, right? Turbulence. So, or rotor clouds. We see that a lot. So mountain breeze is the exact opposite of valley breeze, once again. So we don't really need to spend a whole lot of time, right? Just the air coming down the mountain slopes is cooling, and as it hits the valley, it's heating up and rising over the valley. So let me see. Forgot to show you guys these two videos here. Let's just keep going, and then I'll have you guys watch those videos for homework. We'll end about 15 minutes early so you guys can watch those videos. So let's talk a little bit about heat and temperature here. Okay. So temperature is one of the most basic variables used to describe the state of the atmosphere. We know that air temperature varies with time from one season to the next, between day and night, and even from 1 hour to the next. Air temperature also varies from one location to another, from high altitudes and latitudes to low altitudes and latitudes. Temperature can be critical to some flight operations as foundation for the study of temperature effects on aviation and weather. This chapter describes temperature measurement, and heat transfer imbalances. So we're not going to go over matter and energy, right? So basically matter is the particles. Energy is the particles bouncing off of one another, creating energy. And the product that develops from the energy is heat. Temperature is numerical value representing the average kinetic energy of the atoms and molecules within the matter. So temperature is how we read the amount of heat that those molecules are putting off. Okay. So if you guys didn't know before, we use a thermometer to measure temperature. We have a couple different types of temperature scales. So Kelvin is used to measure thermodynamic or absolute temperature scale, where absolute 0, the theoretical absence of all thermal energy, is 0 Kelvin. Thus, the Kelvin scale is direct measure of the average kinetic molecular activity. Because nothing can be colder than absolute zero, the Kelvin scale contains no negative numbers. So, beakers and test tubes, right? Don't care about Kelvin so much. Unless it's Kelvin Klein. Oh, Kelvin. Sorry, I get those mixed up. Okay, Celsius. Scale is most commonly used temperature scale worldwide and in meteorology. So the scale is approximately based on the freezing point of 0 degrees C and boiling point of water at 100 degrees C. Under pressure, 1 standard atmosphere. So at sea level, water boils at 100 degrees Celsius. So, and freezes at 0 degrees Celsius. So to convert Fahrenheit to Celsius or Kelvin to Celsius, there is your formula. Okay. Fahrenheit is what we use in the United States because we like being different, because this is America. The boiling point in America is 212 degrees Fahrenheit.
Dad?
Yeah, babe.
What's this?
Sorry, child emergency. Okay. So, yeah. Basically, everything we use in aviation is going to be in Celsius. We don't really use Fahrenheit. The captain's job is to convert Celsius to Fahrenheit and then tell the passengers that it's 52 degrees in Fargo, North Dakota. But as far as dispatchers, we don't really care. We plan using Celsius. Just makes our life easier if we don't have to worry about converting it. If you want to learn the formula, go for it. But it's not required. Okay. So here's a comparison chart. Kelvin, 288 degrees is 15 degrees Celsius or 59 degrees Fahrenheit. So this is standard atmosphere at sea level. The boiling point in Kelvin is 373 degrees. Celsius is 100 and Fahrenheit 212. Okay. So heat transfer. Heat transfer is energy transfer as a consequence of temperature difference. Okay. So we saw those temperature differences in lows and high pressures, right? And we see that transfer of heat present itself as cumuliform clouds and convective activity, right? So we'll see the fronts along those heat transfers. We tend to see weather develop. Okay. And going back to Liz, when you were talking about weather being, or the sun being the source of all weather on this planet, here you go. The heat source for the surface of our planet is the sun. Energy from the sun is transferred through space and through Earth's atmosphere to the Earth's surface. Since this energy warms the surface at the air and atmosphere, some of it becomes heat energy. There are 3 ways heat is transferred into and through the atmosphere: radiation, conduction, and convection, or any combination of these. Heat transfer associated with heat change of water from one phase to another can be fundamentally treated as a variation of convective heat transfer. The heat transfer associated with water will be discussed later. So, clouds, fog, other types of precipitation. Okay, radiation. Radiation, if you stood in front of a fireplace or near a campfire, you felt heat transfer known as radiation. The side of your body nearest to the fire warms while the other side remains unaffected by the heat and you freeze to death. Although you are surrounded by air, the air has nothing to do with this type of heat transfer. Heat lamps keep food warm. There needs to be a comma there. Heat lamps that keep food warm work the same way. Okay. So, radiation is the heat or the transfer of heat energy through space by electromagnetic radiation. These waves travel at the speed of light and are usually described in terms as wavelength or frequency. So these are your different types. So X-ray, ultraviolet, visible, infrared, and microwave. So we all emit energy, and as the heat energy with the object is converted to radiation energy. This transmitted radiation passes through entities such as air, water, or space along the way the radiation can be reflected, which occurs when the wave energy changes direction with the encountered object. Okay, solar and terrestrial radiation. So when the sun actually is pounding down on the Earth, we see radiation heat transfer. So we'll talk about why radiation is important for the development of weather. Okay. So the frequency of the sun or hotter objects emit with shorter wavelengths, whereas cooler objects emit with longer wavelengths. Okay. So the frequency is a lot higher. When we talk about frequency, we're talking about taking from one point in time to another point in time, how many times does the frequency, how many times does the wavelength oscillate? That's your frequency. So 1, 2, 3 times, right? Whereas in that same amount of space, we have one oscillation. So that's when we talk about frequency, that's what we're talking about. Some of the solar radiation that reaches the Earth's surfaces is radiated back into the atmosphere to become heat energy. So, yeah. So the solar zenith angle, so insolation is maximized when the solar zenith angle is at 0 degrees, which means the sun is directly overhead. With increasing solar zenith angle, the insolation is spread over an increasingly larger surface. So the insolation becomes less intensive. Okay, this is why we see such a temperature difference between Bermuda and Alaska. It's because of that zenith angle. Conduction is the transfer of energy by molecular activity from one substance to another. Okay, so think of like a soldering iron. I don't know, is that a bad example? But basically the transfer of energy when one substance touches another. Okay. So during conduction, the warmer substance cools and loses heat energy, while the cooler substance warms and gains heat energy. Think of when you get a big old cup of ice and you pour water on it. That's conduction. The way we see it represent itself here on Earth is, let's see, conductivity is a property of substance that indicates the ability to conduct heat as a consequence of molecular motion. Units are watts per meter Kelvin. Note that air is a poor thermal conductor. Okay, so silver, great. Gold, even better. Copper, pretty good stuff. Okay. I will say that water, so I made the mistake of, I was doing dishes and stuff. I use a cast iron skillet. And I took a wet dish rag. So it was the rag I was using to dry dishes. I took that and pulled my cast iron skillet out of the oven. That was a really bad idea. Super good conductor. Instantly turned to steam and burnt the snot out of my hand. But here you can see that apparently steam is a bad conductor. Oh no, it burnt me pretty good. So convection. I've talked about convection a lot. So convection is the transport of heat within a fluid such as air or water via the motions of the fluid itself. This type of heat flow takes place in liquids and gases because they can move freely and it's possible to set up currents within them. Water boiling in a pot is an example of convection. Because the air is a poor thermal conductor, convection plays a vital role in the Earth's atmospheric heat transfer process. Okay. So here you have the three different types of heat transfer. You've got radiation, which is the heat source. You have conduction, okay, and convection occurring within the liquid itself, creating the steam.
Dada, can I give her?
All right, so the thermal response. Whether radiation, conduction, convection, or a combination of these, the temperature response to the input or output of some specified quantity of heat varies from one substance to another. Okay. Specific heat capacity, known simply as specific heat, is defined the measure of heat energy required to increase the temperature of a unit quantity substance by a certain temperature interval. So specific heat capacity is typically expressed in units of joules per gram Kelvin. Okay, there you go. There's your formula. Thus, two different substances with identical temperature measurements do not necessarily possess the same amount of energy. When exposed to the same amount of heat energy, a substance with a low specific heat capacity warms up more than a substance with higher specific heat capacity. Don't ask me to translate that into layman terms. So, heat capacity.
Dada, Mom needs to know.
All right. So there's your thermal response, right? These are the various substances. You can see the response using that formula. So I'm not 100% sure on what all that means, but hey, it's pretty good, right? So I promised you guys 15 minutes to watch those videos. Why don't we call it a day here? This is an easy spot to remember. Go to the Google Drive and pull up the video links in week 4, day 3, and watch the Cloud Types, Jetstream, and Coriolis Effect videos, and we'll continue this discussion tomorrow. So anybody have any questions leading up to now?
Do you recommend any Bill Nye videos for this?
I don't have
it sounds
any
funny, but sometimes it helps when you have something reduced to a child explanation.
Yeah. So I don't know. I would look up thermal response or heat transfer, or look up conduction or convection, radiation, things like that. He may have something.
Okay.
I'd just look up the keywords and see if anything comes up. Bill Nye.
I know he has like whole weather videos. They're only like 28 minutes long.
But
so Garrett, just a quick review: low versus high. I've always imagined, because lows, on a weather map as you're watching the news, are indicative of weather heading my way, so to speak.
Yeah.
And highs seem to block the lows from coming in a lot, and they go up over the top of us. That's why we're so dry in this area. Is it So when I've been thinking about it, trying to figure out the difference between low and high before this, is it safe to say that low pressure literally is just that air rises because the pressure is not very high, and air sinks in a high pressure because of the fact that it's literally holding down things because it is a higher pressure? Is that the way to think about these now?
Yeah, I mean, that definitely falls in line with what we've been talking about. Just remember that, like I said before, those low pressures are always trying to move above the high pressures. Warmer area, when we talk about the volume and the amount of molecules in a body of warm area versus colder air, and the amount of volume is reduced with colder air, you can see that exactly what you just expressed, right? You have the larger volumes, so there's less pressure, versus the high pressure where there's so many molecules compacted into a tighter space. So that pressure is greater. And those low pressures are always trying to roll over the top of those high pressures.
You're saying over the top vertically, not over the top north from south?
It's, vertically.
Okay.
So, and that's when we were talking about the sea breeze and land breeze and stuff like that. That's exactly what it's showing, right? You always have the high pressures trying to overtake those low pressures always trying to overtake the high pressures. And where we see the weather formation, it's always on the edge of the low pressure and high pressure border. Does that make sense?
Yep.
So.
Thank you.
Yeah. Any other questions or? All right. Well, we'll call it a night, guys. Thanks for hanging out.